We present learning from physical human feedback, an object-centric, one-shot adaptation method. Two major challenges face robotics today. First, people's preferences for how to solve a task can vary, such as leaving a cup to dry upright or upside down. Second, the environments that robots work in can constantly change, affecting the desired task behavior, such as leaving a pan flat over a towel or horizontal in a drying rack. Third, the tasks robots are told to complete can be completely arbitrary and unknown beforehand, such as pouring cereal into a blender. As a result, correct behavior for a robot isn't always fixed and needs to be adaptable. As humans, we need to be able to give feedback to robots to either fix wrong or outdated behavior according to our preferences, or have them solve new tasks. Feedback can take different forms, but here we consider physical pushes and pulls because they are intuitive, easy, and expressive. The key question then becomes, how can robots quickly and effectively learn from physical human feedback? In the domain of online learning from human feedback, prior works model human behavior as optimizing a cost or reward function j over a trajectory x. Given the correct objective, desired human behavior can be generated. Prior works define this function as a linear combination of basis functions phi of x with relative weights theta. Such basis functions are predefined, such as the distance to a pre-specified object or error from a desired orientation r star. However, what if new objects are introduced to the task? What if the desired orientation r star changes? The predefined basis functions may not cover changing human preferences, which is problematic when robots are deployed to new environments and tasks. This leaves us with two challenges to solve. How can we handle interactions with new objects efficiently? And two, how can we avoid predefined basis functions phi of x? To address these challenges, we need to draw from our insight and make reasonable simplifications. Our intuition is that most complex long-horizon tasks are really a sequence of simpler subtasks focused on specific objects. When giving feedback, we are likely focused on the robot's interaction with the specific object. As a result, feedback should update behavior with only a specific object, such as the distance to maintain from it. The robot's general behavior should not change, however, such as the overall ability to stay close to or away from any object. To distinguish between object-specific and general behavior, we treat each object as a node in the graph, with a single edge connected to the robot. Edge information is specific to each object, containing both learn features C and state features B that are derived from robot, object, and goal states. How are new objects handled? Simply by adding new nodes to the graph without any change to the computation pipeline. How does this avoid predefined basis functions? Features C are learned, which enables basis functions to be freely defined to capture diverse behaviors. To capture this graph computation in a fully differentiable manner, we use a graph neural network. Specifically, each object robot edge is separately fed through a relation network, FR, to produce edge features E. These are aggregated to overall compute actions composed of a direction of translation V, as well as a desired orientation W. For this process, the model needs to learn two things: how to generally interact with objects based on proximity, and how to capture specific object behavior. To ease the learning, we train these aspects separately in two phases. In the first phase, we train the model on how to generally interact with any object. In phase 2, we deploy the trained model into real-world scenarios where adaptation to human feedback is necessary. Here, the general model fine-tunes its behavior for a specific task. The parameters learned in phase 1 are separate from those adapted in phase 2. To learn general interaction dynamics, our model is trained to imitate expert trajectories. Rather than collect expensive human demonstrations, however, we choose to synthetically generate cheap but diverse trajectories that capture our desired behaviors. This is possible because of our insight that many human tasks are object-centric. Overall, through this process, we have reduced our original network parameter space into that of general dynamics and that of object-specific behavior. In Phase 2, our model must adapt to real human feedback. The only assumption we make on such feedback is that the human is demonstrating some preferred behavior, whether this is fixing wrong behavior or demonstrating a new desired task. Based on this assumption, we treat the human perturbation as an expert demonstration and imitate this with the same loss used in Phase 1. By backpropagating gradients from this loss, we can run standard gradient descent to update our model's parameters. Rather than naively fine-tuning all parameters, however, we take advantage of the separation between general and object-specific behavior that we achieved from Phase 1. We freeze the general dynamics weights and update only object-specific features to change object-specific interactions. This is the key to allowing fast, online, and effective adaptation. By optimizing freely in the object feature space, our model can learn new behaviors never seen at training. Freezing the general dynamics also prevents catastrophic forgetting, or degradation of previously learned behavior with other objects. To evaluate performance, we invited 10 participants to interact with our system on 3 tasks. In Task 1, the robot should learn from human corrections to stay low to the table as it carries a fragile cup to a goal location. Originally, the robot will move straight to the goal. Participants can freely perturb the robot at any moment, and ideally the robot should learn from these pushes to stay low as long as possible. This task evaluates our method's adaptability to position preferences, specifically attraction to or repulsion away from objects. Task 1 also highlights our method's fast adaptation, which happens in real time when users finish applying perturbations. This video shows the baseline that we compare against, a non-adaptive controller that always moves straight to the goal. The user can take control at any moment and release control when satisfied with the current pink cup's position. The task involves 3 separate goal positions, and overall, the less human effort, the better. This video shows the same task as before, but with our method replacing the baseline. As the user releases control in the next frame, our method will adapt to the past series of perturbations in real time, giving us the updated behavior that we'll see. Although not shown here, if a user feels a robot lingers too close to the table, they can just as easily express this preference with an additional perturbation, meaning that our model's adaptability is continual and is not stuck after the initial one-shot adaptation. Here we examine the overall end effector trajectories, where either the robot or the human was in control. We compare the left non-adaptive baseline with our method on the right, using 2 metrics, distance to the table and overall human effort. As shown in the figures, our method significantly outperforms the baseline in these metrics. These next videos show the same task, but with a different user. We only show one trial to be concise. Looking at the final trajectories, we see that our method can easily handle different users. In Task 2, a robot presents pans for quality control inspection. The human perturbs the robot to hold the pan in different orientations. The robot should match this orientation in the next iteration. While the previous task adapted position preference, this task adapts orientation preferences relative to the inspection tray and highlights our model's ability to quickly learn arbitrary orientations. Here, the user is actively perturbing the robot's orientation so the pan is held correctly. Now we show the robot's updated behavior and judge whether it presented the pan according to the user's preference shown in the top right. Although this task can be solved by literally memorizing the desired orientation, this task is meant to demonstrate our model's ability to reproduce new behaviors never seen during training. In this case, arbitrary orientations using only a few steps of gradient descent. This cannot be handled using a finite set of predefined basis functions. Here we show the results of the same task but with a different user. We can see that our model matches the user preferences reasonably well. In task 3, the robot originally carries bowls straight to a drop-off zone. The factory has installed a new scanner to scan the bottom label of each bowl. The user needs to perturb both position and orientation of the robot, so that the robot learns this new intermediate subtask of scanning each bowl. The user sees the robot's original behavior. Here, the user is actively perturbing both position and orientation of the robot to demonstrate this new subtask of scanning each bowl. We now see the robot's updated behavior and judge whether it correctly scans each bowl. Here is the same task but with a different user. Although this task can be solved by prior works, this task represents our model's ability to learn useful, real-world interactions with any new object without needing to be defined beforehand. Overall, we wish to emphasize several key takeaways. First, robots can be pre-trained to complete any number of tasks, but there will be a scenario where their behavior is incorrect, at least according to someone's particular preferences. As a result, robots need to be able to learn and adapt from human feedback. Second, human intentions can be difficult to parse, even for us, but this can be simplified greatly by framing human intentions and tasks as object-centric, or involving an interaction with a specific object. This certainly doesn't capture all tasks, but does describe many. Using this insight, we represent the environment as a graph with nodes as objects connected to the robot. This graph representation is what allowed us to separate general behavior from object-specific interactions, allowing us to freeze the general network weights and adapt only object-specific features. This was key to allowing fast, online, and effective adaptation to new behaviors never seen at training. This also allowed us to use simple gradient descent for adaptation without suffering from catastrophic forgetting. Our experiments showed that our approach works well on realistic tasks with real human feedback. Our method is by no means perfect and ignores other complex challenges such as dexterous grasping and non-object-centric tasks like acrobatics or drawing. However, we hope that this work inspires others to either extend the domain of learning from human feedback or provides useful insights in how to better optimize deep learning models in other domains.